So far, we've talked about a bunch of different classification methods. Neural networks was an example. The other one was decision trees. Those methods were fairly complicated. However, there is another method that I'm going to go over today called KNN or K-nearest neighbor, which is very simple. However, despite its simplicity, it produces really good results when it comes to accuracy of classification. It is comparable with neural networks and decision trees. Um, it is a type of instance-based learning or lazy learning, which means that it is so simple that most of the work in terms of computations take place at the time of the prediction, not at the time of the modeling. And when we're talking about KNN or K nearest neighbor, the K refers to the number of the neighbors that are used to conduct the analysis. And let me describe the method using a very simple example for you. Suppose that I wanted to know what is your favorite actor. Uh, However, I didn't want to ask you specifically. One way to infer whom your favorite actor is to ask your closest friends. So if I go and find three of your best friends and ask them about whom their favorite actor is, and suppose that two out of three, which in this graph is shown by, say, blue dots, say that Brad Pitt is their favorite actor, then I can say that there is a very high chance that your favorite actor is also Brad Pitt because you are uh, close to those two friends. In this particular example, k is equal to 3 because I've asked three of your friends. And I'm saying here that the answer depends on the value of k because if I expand the circle of friends and go from 3 to say 5 in order to ask the 5 of your closest friends about their favorite actor, and then 3 out of 5 say that their most favorite actor is Ben Affleck, then I'm going to say that, all right, I would classify your favorite actor to be Ben Affleck, right? So the answer changed when I went from 3 to 5. As you can see here, it is very important to be able to calculate the distance between each point and the other observations in the data set, primarily because we want to identify the nearest neighbor. So as soon as we start talking about nearest, then the dimension of distance comes into the picture, right? How are you going to define somebody who is near or far from you? You have to have a measure of distance. And there are different metrics for distance. Manhattan or distance is one of them, and Euclidean distance is another of them. I'm going to show you a very simple example of Euclidean distance. But simply speaking, you're just basically taking the coordinates difference and then take them to the power of 2, add them together, and then finally take the square root. Now, how does it work? Well, suppose that you have 2 points, point P and point Q, right, on a two-dimensional space. So the coordinates of point P are P1 and P2. Specifically speaking, P1 is equal to 3 and P2 is equal to 2, right? So these are the coordinates of the first point. In other words, these are the features of the first point. You can think of them as height and weight of one observation in your data set. The other point, the point Q, also has its own coordinates. In this specific example, Q1 is equal to 7 and Q2 is equal to 4. Now, if you want to calculate the Euclidean distance between these 2 points, you simply say it's going to be 7 minus 3 to the power of 2 plus 4 minus 2 to the power of 2, which is going to be 20, and when you take the square root of 20, it's going to approximately be 4.47. In other words, the distance between the points P and Q is calculated to be 4.47. So going back to the original example, what you have to do for K-nearest neighbor method is to calculate that Euclidean distance between the point of interest and every other point in order to be able to calculate, to determine the K-nearest neighbors. You basically want to see which of these points have the shortest distance to your point of interest, and then see what is the classification of those K-nearest neighbors, and whatever that was would determine what is the classification of the new point or the point of interest that you're interested at. So one last thing before I go into an example to show it in application is that how are you going to determine the number of the neighbors? Basically, given the fact that the result depends on what is the value of k, whether it's 3 or 5 or 4 or 2 or 1, right? How are you going to determine the value of k? Well, like many other questions, the answer is it depends. And here it depends on the data that you have and the context that you have. Larger values reduce the effect of noise, so you go and ask more people in order to have a better understanding. However, it makes boundaries between classes less distinct. Basically, you're going to say everybody is similar to each other, right? You won't be able to have distinct boundaries or distinct classification in your model. And the optimal value of k basically could be found heuristically. When in this example, when we go back and say that, all right, your classification of most favorite actor, let's say, is Ben Affleck, we can then compare the accuracy of this classification with real data, because in classification is a supervised learning. So we have the correct answer, and from there we can calculate the error, right? So we can say that, all right, out of 10 people whom we had to figure out their most favorite actor, using k equal 3, we could accurately predict the favorite actor of 7 people, whereas when we went from 3 to, say, 5, we could only accurately predict the favorite actor of 2 people. And based on that observation, it seems like the better k to be considered is the first one that gave us the higher accuracy. So again, it is something that you can use data in order to figure out, in addition to the context that you're working with. You don't want to increase the number of k's too much, but you don't also want to reduce it too little, such that your accuracy suffers. You have to strike a balance between those two aspects. So let's go to Excel to show you how simple it is to conduct this K-nearest neighbor analysis. And let's start with a very, very simple example. Suppose that you have an online store that sells clothing, and you want to create a service or basically an algorithm that is going to recommend the appropriate size of a particular clothing item to your customer based on their height and their weight. So what you have done is that you've gone back to your previous purchases and figured the association between height, weight, and the size that your customers previously indicated was appropriate for them. And this, suppose, is the data set that you have. So You have the weight of your customers, and suppose that I'm talking in terms of kilos, so 55 kilos and so forth. Or let me change it to pounds, and it's more relatable. So hold on a second. So let me just say weight multiplied by 2.2 is the weight in pound. So I'm going to use this instead of the kilo. And then I have the height in centimeters. So a person who weighs 121 pounds and has a height of 160 wears a size S, standing for small, whereas a person who weighs 198 pounds is 190 centimeters tall, wears a size L. Right? So you have this data set, and what you want to do is to say that a new customer comes and they give you their weight and their height, and what you have to do is to determine what their size should be. All right? So that is in essence a classification. Why? Because there are three possible classes that you could put a particular customer in. And let's say that this is a person who weighs 150, and the height of this person is, let's say, 170, right? So we are going to figure out what is the appropriate size of clothing for this person. And again, it is a classification problem because you have three potential classes that you can put that person into. You can say, oh, you're a size small, or you're a person with a size M for medium, or you're a person with size L for large. So the task at hand is to figure out a way in order to correctly classify that new person. Well, the very first thing that you have to do is to calculate the distance between this new person and every other observation in your data set. So what we are going to do is to type in the formula for Euclidean distance. And if you remember, I said that it is the square root of the difference between the features of your point of interest and the features of every other observation. So basically what I have to say here is that it is equal to the square root of 150, which is this value in the cell D2 in my Excel sheet, minus whatever the weight is for the first observation, which is in this particular cell, A4, and that has to be to the power of 2, plus the same thing for height. The height of this new person that you want to classify minus the height of your first observation, and that has to be to the power of 2. And now I'm going to close the square root. So this 30.67 is the Euclidean distance between your new person and the first observation. Now I have to expand it to all the other observations. So what I am going to do is that I'm going to put a dollar sign around the cells that correspond the weight and the height of the first person so that it doesn't change when I expand. And then it is going to automatically change the other values. So for example, the very last row here is showing the Euclidean distance between my point of interest, which I am going to code it like this, my point of interest, or my person that I want to classify, right? So here, for example, I have the difference between the weight of this person and the last person. So D2 minus A13, D2 is 150 minus A13, 198, to the power of 2, whatever it is, plus F2 minus B13, and F2 is the height of the person that I want to classify, and B13 is the height of the last person in my data set. Whatever that value is, to the power of 2, I add them together and then take the square root, which is going to be equal to 52, according to Excel. Now, all right, so let's also put a name for this column and say that this is our distance, right? The next step that we have to do here is to figure out which ones are basically the closest distance to what we want. So I am going to use the rank function, and I am going to say, well, rank this distance within this column, and because I want to expand it, I have to put $sign so that it does not change. And then the next one is to determine whether I want ascending or descending. In this case, I want ascending. So here, this person is rank number 7, whereas this person is rank number 1. And what happened here? D14. Oh, here. Okay. This should be D13. Okay, let me see. Oh, sorry. So here it's the problem. So I have to rank D4 here. All right, so let me redo it. All right, so you can see that the ranks are shown. So rank number 1 is the closest neighbor, which has the closest distance, or the smallest, shortest distance between the person whom we want to classify and the other observations, right? So here we have 1, 2, and 3, and these 3 are actually the first, say, 3 neighbors, or if k was equal to 3, this would be the 3 nearest neighbors, right? And look at their sizes. They are all wearing size M, and therefore the classification for the size of this new person would be M. That's it. Now let's think about another example. Let's say that the guy was 250 pounds and was quite tall, let's say 210 centimeters, right? Now, what are the closest neighbors? Well, it's going to be some different ones. And when you look at here, you see that 1, 2, and 3 are now these last 3 ones, all right? And what is the size of these last 3 ones? They're all large, right? So this guy is going to be a large person, going to be wearing a large size, right? So this is how easy the method is, and it's so easy that you can apply it in Excel fairly easily. What is important to understand is I only used two features here, right? Weight and height. It does not necessarily need to be restricted to 2 features. You can increase the number of features to as many features as they are. The only thing that you have to do is that you have to expand the distance formula so that it is going to consider the distance between the 3rd feature, the 4th feature, the 5th feature, all the way to whatever number of features you have, right? So suppose that I had weight, height, and I wanted to add another variable that identifies if the person is male or not, right? So it would have been 1 if the person is male and 0 if the person is female. And I'm just haphazardly putting in numbers here. And so the new guy or the new person that comes has a weight of, say, 250 and the height is 210. And we also know that that person is a male, right? So what you have to do here is to expand the formula for distance so that you are also going to include the distance for the genders, right? So this is going to include the distance between whatever the value is in F2 minus the value of C4, which is representing the gender in your in your data set, right? And then you can just expand it so that you're going to have a slightly different distances. It still turns out to be that these last three people have the shortest distance. Now, if I had changed it from male to female, then you see that these values change. And if it was, let's say, 140, then the closest neighbors would change accordingly. So this is the first one, this is the second one, and this is the third one in terms of distance. And when you look at here, this is actually a very good example because the size is not consistent among all the three. So two of them have large, whereas one of them has medium. So the way to go about this is to see which one is more common. So 2 out of 3 are wearing large. So that for this person, you're going to say that, okay, the size is also going to be large. So that is how KNN method works.